Okay, first of all, thank you for joining today's Research Trend AI sessions, whose theme is reasoning in language models and LLM agents. So first of all, to kick things off, we're focusing on reasoning by LLMs in the context of morphology and multilingual settings, particularly across 41 raw resource languages. It is my pleasure to introduce our first speaker, Mukund Choudhary, who is a PhD student in NLP at Mohammed bin Zayed University of AI. His PhD research investigates how LLMs model language or LLM linguistics, and this is his first work in a series of upcoming works exploring how LLMs structure language differently than humans and what can be done next. And in his latest paper, Unveiling What Makes Linguistics Olympiad Puzzles Tricky for LLMs, he and his team built a benchmark of 64 puzzles across 41 raw resource languages. Annotate each puzzle with 50 typological and linguistic features, then evaluate 10 different strongest LLMs. They showed that morphological complexity, topological distance from English, and tight evidence constraints each substantially degrade model performance. Furthermore, they demonstrate that explicitly tokenizing and morphing boundaries improves results. So please join in welcoming Mukund and his insightful work published at COLM 2025.
Thanks, Yein, for that introduction. That was pretty exhaustive. Okay, I hope you all can see my screen and that you can hear me well as well. So,
Yes.
thank you. So, yeah, my paper is titled Unveiling What Makes Linguistics Olympiad Puzzles Tricky for LLMs. So, we know from a very recent standpoint that there are like 3, 4 publications out there which kind of try informatics Olympiads, mathematics Olympiads, and so on and so forth with LLMs. And LLMs generally perform well, good enough. We also know from a couple of research that linguistics Olympiad is a tricky place, and mostly LLMs cannot do more than 40 to 60% on problems which high schoolers can do about like 100% of. So these puzzles are very interesting, and I'll get to why they are interesting. But what excited us most was not how LLMs performed, but why these puzzles were difficult for LLMs. We wanted to see what makes this kind of linguistic reasoning difficult for large language models. And that's why we picked up this problem statement to begin with. Okay. So a typical linguistics puzzles looks like this. There is some in-context data, which is like, let's say, 6 parallel translations between English and a highly low resource language, which most human participants who are high schoolers would not have known, seen, or learned in their lifetimes. And as a result, LLMs do not have a lot of understanding of these languages as well. We do a contamination check to make sure that LLMs do not really know about these languages. But yeah, but basically the idea is that these are highly low resource, so LLMs cannot really memorize what's up with them. So there is some data which is parallel, which means whatever this sentence means is the same as this sentence. And then there are some puzzles which are from the same kind of distribution, use the same kind of words, and you're supposed to translate in either direction, either from English to low resource or low resource to English. So this is a typical setting of a linguistics Olympiad puzzle. Now, this is a very interesting paradigm because one, it is all in context. So you don't need external knowledge to be able to understand what's happening with the language. All information that you need is present in the data that is given to you. Second, it is also something which does not include memorization. So you cannot really learn all of these things. You have to reason through linguistics. You have to reason through language like a field linguist does, and like children do when they look at like a new problem like this. And third, this was also very interesting to us because this is ensured to be highly solvable. Just this much amount of data is pilot tested by a bunch of people, and then students have already solved this on like other high school Olympiad rounds. So we know for a fact that these are 100% solvable given just this much amount of information. So these are extremely curated puzzles, which has all information they need. So if the LLMs can really reason as we think they do, then they should be able to solve these puzzles as well. So we were trying to see why LLMs generally do not perform well. And we started with a benchmarking again to just see that given research is the same as what we see. And we saw that DeepSeek R1, I mean, this work was done around 2024 April. And at that point in time, DeepSeek R1 was the quote unquote best model in terms of reasoning. And that is what our benchmarks also showed, that it obtained up to 60% across all puzzles that we got, like an on average accuracy of 60%. And then you can see the accuracy kind of drops across GPT-4, 4.0, 3.5, the Llama family, which is from 3.1, and then there's like Llama 2 results as well, which is like even lower. And we also tried it with Mixtral. So we tried to have diversity in terms of open and closed LLMs, reasoning LLMs and non-reasoning LLMs, and also in terms of sizes, which went from 7 billion to all the way to like GPT-4 and 4.0, which are like the highest. So these are the diverse kind of LLMs that we try to put in through the entire benchmarking. And no model got more than 60% on an average. And when translating from low resource language to English, that was the highest score, which is about 68% from DeepSeek R1. So this is like a overall idea of how LLMs are. And just to remind you in context that most high schoolers solve like 100% in this. So they would have gotten like 100% accuracy in about 2 to 3 hours of problem solving time per 5 to 6 puzzle sets, 5 to 6 puzzles, a set of puzzles. So yeah, so in general, this is very solvable, but you can see that they are not really solved well. So to understand what makes this difficult for LLMs, we try to annotate these puzzles in terms of what linguistic features they had. So for example, in English, the word order is subject and then object, and then, sorry, subject, verb, and object. But in this language, this low resource language Bangi made, the order was subject, object, and then verb. So one of the features extracted was the word order, and the second was this prefix. So in this language, the main puzzling part was that there is a different word order. And the second part was that the verbs have prefix for the third person plural subject, which is we in English. So they have a special ne prefix, which is added to the verb. So otherwise, the verb would look like without prefix, it would just look like the verb root itself. So there's an extra prefix that English does not have, and there's a change in word order. So these are the two features that we extract. And then we classify it into different categories like syntax, morphology, all the linguistic categories. And then we also annotate for, is this feature present in English or is it similar to something that is present in English? And then finally, we also check for how much data is present in this puzzle, which is reflecting that kind of understanding. So for example, word order is reflected in all of these examples. So you have like 100% redundancy. So it's not context constrained. But at the same time, for prefix, there's only exactly 2 examples, which is the bare minimum examples you will need to understand what's happening with the prefix. So it is very context constrained. So we basically annotate for context redundancy, how much redundant data is there, is the feature present in English or not, and what kind of feature is it? Is it a syntactic feature, morphological feature, and so on and so forth. So we annotate for all of these features using World Atlas of language features. And there were like about 50 features that we came up with, and there were about 2 expert annotators who had some experience with linguistics and who were previous Linguistics Olympiad participants. What we found out by doing a correlation between scores and these features was the following. 3 main findings. There were other findings which were not very strongly correlated, but the 3 main findings which had a very strong correlation were these. One, LLMs have an English bias. So any puzzle which was more English-like, as compared to a puzzle which was less English-like, was easier to solve for LLMs. So for example, in this puzzle, if the word order was the same as English, blue, green, and red instead of blue, red, and green, then this puzzle would have been easier to solve for an LLM. So in general, puzzles which were more English-like linguistically were easier to solve for LLMs. Second, LLMs needed redundancy. That is, the more data given to it in the in-context sample here, if I gave it like 2 more examples from the same distribution, it would have been easier to solve for LLMs, regardless of what kind of data it is. If it is from the same distribution, it helped it solve the puzzle better. So for example, in this puzzle, 1, 2, 3, 4, and 5, these 5 samples were good enough to like solve and figure out what's up. But when we add two more examples, it became like 100% solvable for mostly all LLMs, except for the smaller ones. So redundancy helps. And third, which was the main major finding and which we experimented with like a post hoc study as well, was that LLMs find morphology tricky. So any puzzles which had a set of features which were about morphological complexity were tougher for LLMs. That is, any puzzles which had words which were composed of a lot of prefixes, suffixes, which needed to be tokenized and broken down. Those languages were generally tougher for LLMs. What this meant for us was that maybe it's not tokenizing it right, and maybe that's why the reasoning is like snowballed wrong. What we did was to do a pilot study by separating out the prefixes and the roots by spaces to see if that helps. So we basically made it explicit that these are the units of the word you need to focus on, and then tried to like redo the experiment, and we found out that the scores got much better for all of these morphologically complex puzzles. So you can see from this example that the same puzzle, which was basically this puzzle, we separated this pink slash is basically where we separated out the morphemes. So we separated the morphemes and everything in the explanation and the answer was the same, except for the one thing it got wrong, which was the morphology. So the red portions of the explanation are the older explanation, and the green portions are the new ones. Everything else is the same in the explanation. And you can see that the parts where it had NE as a prefix, it got wrong. It kind of clubbed it with the existing word. But when we separated it out and gave it to the LLM again to solve, it figured out that NE is a different word and NO is a different word. And then it solved it right, and then it got the translations right as well. So yeah, these were the major findings, and this is what our work was about. If you have any questions, concerns, doubts, you may ask.
Okay, thank you for presenting your amazing work. And let's get to start the Q&A sessions. First of all, I would start this Q&A with my own simple questions. Like the first one, did you also consider reasoning difficulties in the puzzles apart from the linguistic features? Like, do you think they would interact with each other and make the puzzles more complex for LLMs?
That is a good question. That is actually a limitation of our study. So, any linguistics Olympiad puzzle has two problems in it. One is the linguistic feature itself, which we explored, and the other is the reasoning process that we need to do. So, mostly students solve it by a frequency pattern matching. So, you see the word, let's say, you see the word V twice, and you see the morpheme NE twice, and you figure out that, oh, this is what the mapping is. But if the frequency is not enough, then you go by process of elimination or something else. So these reasoning activities and processes are what make a puzzle even more tougher. But we did not explore that angle because we did not have enough grounding for it, and the limited set of puzzles that we had did not have enough variety in terms of reasoning processes. But that will be a topic of a follow-up work eventually about complexity of like puzzles and in general complexity of NLP tasks and how to measure those complexity and how to measure all NLP tasks on like a common benchmark in terms of how complex each of the data point in a data set is in a benchmark is and how complex a task is as compared to another task. So complexity and reasoning variables are really difficult to grasp, and that's why we did not touch upon in this work, but we will do it in a follow-up work. Yeah.
Okay, thank you for answering my questions. And so for the next, is there any questions from the audience?
I also have one question, but more broadly, because I don't know much about linguistics Olympiad. So this is an Olympiad that's designed for humans, right?
Yes, high schoolers.
Um, what kind of cognitive abilities are they looking for when they present these questions?
Nothing, it's just reasoning. So high schooler students who have no exposure to linguistics, who have no exposure to these low resource languages are supposed to solve it. So they can be as low as like sixth grade students who have just started to learn like, let's say, basic social science, STEM subjects, and they can also solve these questions. It's
Mhm.
just reasoning. If you're good at reasoning and figuring out how language works, you're fine.
I see. So would you say like most of it is essentially deducing the logic behind the linguistic patterns, rather than kind of relying on knowledge that is learned by heart.
Absolutely, yeah. So that is the point of these Olympiads, that if you are able to memorize something, then that puzzle will not show up here. So it will not be a puzzle about, let's say, English linguistics, because that's something that we all learn. It's going to be about a feature, linguistic feature, which you have not seen before from a language that you have not seen before. So it is more about deducing than memorizing that this kind of feature might exist.
I see. Yeah. Yeah, that answers my question. Sounds good.
Any other questions? Okay. In that case, I think we should move on to the next presentation. And I will be introducing Yein and what he's going to talk about today. Okay, so we have just examined how linguistic complexity, especially morphology and limited data, can challenge even our strongest models, including reasoning models, as illustrated by our analysis from linguistics Olympiad puzzles. Our next speaker, who is Yein, takes that question inside the model itself. So, what happens within a model when it tries to reason? Yein Park from Korea University's data mining, sorry, from Korea University Data Mining and Information System Lab, studies the mechanistic circuits of reasoning, how post-training literally sparks new attention heads that coordinate logical steps, and how these reasoning circuits explain both success on complex problems and failure on simple ones. His broader work connects across temporal reasoning, retrieval guided question answering, and chain of thought interpretability, probing when model thinks and how they recall time bound knowledge, and how reasoning sometimes goes off course. This talk marks one of the first steps towards his broader agenda from the POV of interpretability to post training, applying interpretability driven insights to post training models. Today, in his talk about emergent reasoning circuits, Yein will show us how post-training transforms a model's architecture, turning static networks into dynamic systems of thought, and how understanding how these circuits might help us design that reasoning as elegantly as they recall. So, yeah, over to Yein.
Okay, thank you for introducing me, Mukund, and I will share my screens. Yeah, you can see the screens, right?
Yep, it's visible.
Yeah.
Okay, I will start again with the total name of research. The name is like Thinking Sparks and Emergent Attention Heads in Reasoning Models during Posted Training. And my name is Yein Park, and I'm a master degree student of Korea University and currently preparing PhD for the next semester. And today's content is like this, and let me just go through to the introductions. And for the background, I would like to share my core research topic. It is named as From Interpretability to Post-Training, which means I would like to question that how the internal mechanisms of LLM handle each specific tasks. And so that is why I started from the insights of research on knowledge, especially for temporal knowledge. And then I develop the ideas like evaluate knowledges and then find out what is the internal mechanism of that kind of processing knowledges. And then I go to the next step for using that insight of interpretability to the post-training methods. So the our goal of my research is like the designing a interpretable analysis to trace models into computation, then aim to inform and refine subsequent training and alignment methods. So today's topic, the reasoning circuits, are focused on the circuit level analysis with diverse post-training methods and reveal that emergent reasoning specific attention heads for complex tasks. So, and then I also plan to devise fine-grained post-training methods with robust, but without trade-offs like using only specific mathematical expressions. Yeah. And also, I would like to here incorporate these insights from today's topics. Yeah, so let me go started with the overview. So you can see the right picture. It is like the overall mechanisms of our analysis. And the reasoning circuits trace the internal computations of large reasoning models. And after post-trainings, newly activated attention heads are usually influence its performance. Like you can see that we can use the prompt from each reasoning needed questions like AIME, the usual answer, and then the assistant use think token to start its reasoning. And I would trace the thinking process through the think token and construct circuits, which is a cyclic graph of internal mechanism transformer, and then I find out which attention heads are especially emergent in those post-trained models. So brief description is right here. Like complex reasoning abilities in LRMs are largely by SFT and RR. But however, these architectural mechanisms behind these gains still remain opaque. So I conduct circuit level analysis to reveal the emergence of functionally specialized attention heads for reasoning after each post-trainings. So these heads are collectively enable structural reasoning and computations, bridging micro-level circuit analysis with macro-level performance differences. And the key findings is right here. Four main post-training methods like distillation, SFT, and GRPO, then thinking on off for recent models. The distillation induced a large number of emergent attention heads, mostly early to middle, and then SFT also introduced a large number of emergent attention heads, but specifically mid to late layer of uh, transformer models. Yeah. And they instill complex reasoning, but can introduce confusion or even redundancy among those heads. And then GRPO, currently known as like DeepSeek training method, engages in a deep dynamic search for reasoning heads during RL training. Like, and they perform minimal yet high impact edits, like optimizing the use of existing ability without creating some novel pathways. And then think on up for specifically, think on mode lacks exclusive heads, but triggers robust reasoning activities. However, thinking of mode activates compensatory heads, which means much more emergent heads when compared to thinking on, then improving short-term performance but reduce reasoning robustness. And I would like to start for the motivations, which is come from my previous research, and it is named as temporal head, which distinguish specific attention heads for only considering temporal constraint knowledges. Like you can see here, the left figure A, that the only the above sentence used the temporal context like in 2019 in 1999, and it affect to the circuit that activate some specific attention head which is not coming to the other simple knowledge circuits without this temporal context. And so we named it temporal head, and its activation is largely connected with the actual displaying the knowledges. And that is why we started this research. Like we would like to use this insight of temporal heads to the reasoning models. Like we also could find some kind of reasoning heads for the using this kind of circuit analysis. So that is why we started from these backgrounds, and then we use circuits, which is decide directed acyclic graph, and here in each node represents a component like attention heads or MLPs or embeddings, and then edges encode how activations flow through the residual streams across each layers. A circuit is also subgraph and explaining specific behaviors like factual records. And we use EAPI version of circuit. It measures contribution of each edge via integrated gradients along activation paths. And it calculates gradient of task agnostic divergence with respect to the input of node V. Then produces an edge importance score averaged over path steps. And here we use the models to construct circuits as consistent family of models for similar architecture and design. So we choose QN, like QN 2.5 mass 1.5B and 2.5 mass 7B. And then its distillation version like DeepSeek R1 distill, QN for 1.5B and 7B. Then we also use the think on-off models like QN3 8B, and then we trained these models for like post-trainings like SFTs or other GRPO. The training data is like open arrow mass 220K and GSM per K, which is a very famous mathematical training data set. And we also evaluate these kind of models and to find out how this emergent set affect to its performance. So we use AIME or AMC. This is very famous reasoning evaluating benchmarks. And the prompt setting that I mentioned before, like as the circuit traces its internal computations through the input prompt, then to predict the first token of output prompt, we sampled each model's answer, like think, starting from the think token, they answer like, okay, so I have this problem, and also ally, so I have this problem, yeah, that kind of things. And then we also sampled some base models answer like we would like to distinguish between the reasoning models and the baseline models. So we used it as a distinguishable mechanism between reasonings and baseline models. And the four main component of my methodology is like here. The first one is circuit mapping. So that we map the activation computation graph for both baseline model and the post-trained model. Then baseline model, we use clean prompt, which is a target prompt for constructing circuits, such as like to determine, which is a sample of the answer from baseline models. Also, vice versa, like reasoning models, we use clean prompt, which is a target prompt for reasoning model, starting right after think, which is already sampled from these reading models. Then we identified some emergent components. It is like much more like finding out and distinguish which head is only seen in these reasoning circuits. And we compare circuits of post-trained models to that of the baseline models for identifying the set of emergent heads. And then we causally validations we using ablations to confirm like causally responsibility. And so we ablate, which is means zeroing out the output of each heads. Then we check the performance difference between the baseline models and the ablated models. We also additionally do some head activation scaling, which means scaling up or down the activation of these founded out reasoning heads in base model to find out is these specifically do for some kind of complex tasks for activating reasonings. So here is the list of emergent attention heads for these model categories. Now you can see that this DeepSeek R1 version shows some emergent attention net which is not shown in the circuits or baseline models, and it counts like 32 number of heads. And also SFT introduces around 34 number of heads, which is a lot much more than GRPO, like it is almost half. Like GRPO with OpenR1 only introduced 19 heads for us for reasoning, and they are only shown in this kind of model specific circuits. And we mapped it in this huge map. We named it as a map of reasoning, which is like mapping all the emergent head in circuits for each different post training. And here you can see that most of the distillation heads are focused on the early to mid layer, and the SFT heads are focused on mid to late layer, which is blue and green in this case. And also GRPO heads are spread through the whole layers, and so also they have some common attention heads. And in here we cannot find out any common for all the methods like distillation, SFT, GRPO. Yeah, we cannot find that kind of head, so we just mapped two different models common heads.
Can I ask a question here?
Oh, yeah, sure.
What's the difference between the above and below?
So the above is the exact using the exact heads IDs and rear IDs, and the down one, like the y-axis, is just heads for the sorted. Like you can, it is just a stacked version of the attention heads. So you can see how many attention heads are emergent in this kind of layers, and colored like showing which is the layer that attention the post training focuses on. Yeah.
A few more questions. So, what is the difference between base model and the gray cells? In other words, I don't see the legend for the gray
Yeah,
cells.
sure, sure. So, base model is just called as white, and here I would like to specify that these heads are not the only head in that these order models, and it is the attention heads from each specific circuits. So that is why I said the circuit is uh, reconstructing the internal mechanism of each LLMs. So it distinguish only the effective and only the important head of each models for doing some specific tasks. So that is why they have a gray spaces, which is not actually does not activate it, but it is just a mapping of attention heads only seen in circuits. So this is not this is different from like the models actually do not use this kind of gray scale circuit attention heads in its activations. Yeah.
Final question. Is it possible for two different types of impacts be placed on the same head? So, for
Oh
example,
yeah,
GRPO and
yeah.
GRPO and SFT, they may actually overlap in some of the heads at the same layer ID and head ID. Is that
Oh
possible?
yeah, sure, sure. It is like we do not like stack this kind of post training. It is just simply coming from different circuits, but uh it's the ID and ID of layer and head is just matched. So yeah, it is not same as like uh the distillation and GRPO doing the distillation GRPO at the single model. Yeah. Yeah, we just found the IDs of each heads and layers, then mapping it to the uh, these four maps, and then yeah, those heads are just simply coming from different circuits. Yeah.
Hmm. Thank you.
Thank you. And if you don't have more questions, then I will go through the next pages. And so we do some in-depth analysis on SFT and distillations. Like distillation heads are strongly effective to performances, like they induces new consistently activated reasoning heads, but do not present in base circuits. And these heads enhance reasoning by building on pre-trained structures, not replacing them. And deactivating, which is been updating, these emergent reasoning heads lead to performance drop across benchmarks. And this suggests that distillation-induced heads are crucial, but can also cause confusion in reaching, which means we also can see some kind of increase of performance when we update those heads. Like you can see the very different ablation types. And here, like the DeepSeek R1 Distill QN 1.5b, the ablation of reasoning heads degraded the performance of these models. But also some base model has can degrade the performance, but the overall drop of the performance is largely effective with reasoning heads. And also some this trivia QA means the circuits with trivia circuits created we using trivia QA, and these heads are mainly correlated with the basic knowledge tasks. And if we apply those kind of tasks, it the performance going to almost zero. And the similar are shown into DeepSeek R1 version of QN7B. And it is interestingly, they also increase the performances when it is updated those heads, especially when we update base model heads in this DeepSeek distilled version, the performance of AIME and GPQA are increased. Also AMC are increased. And down below is the another operation test with base models. Like if we operate base model heads with QN 2.5 s, which is a base model, then the performance drops significantly. Then the models are when operated the reasoning heads. Also, the similar happened with the QN 2.5 Math 7b, and it also shows out that some performance increases with operating reasoning heads. And also we do for the next with SFT, and SFT introduces large amount of attention heads in middle to rate layers, and they steadily produce additional reasoning that persists throughout training. And most new heads emerge at middle to rate layers, indicating structured pathway formulations. We do quantitative analysis and qualitative analysis. For quantitative, we remove 10 to almost 10 mid to rate SFT heads, and it drops all benchmark scores nearly zero. And overactivation reveals trade-offs, like some tasks improve, but others are degraded. Like the mass is increased when we overactivate it, which is scaling up the those attention heads, but some of the other benchmarks like AMC also decreased. So this means just simply scaling up those heads is not the way of this SFT works, and it comes with some trade-offs for these whole emergent attention heads. And we also do qualitative analysis, like SFT models tend to overthink, like using too much longer algebraic paths or detours. And new heads improve structure but reduced strategy efficiency, causing missed solutions. And this is some kind of overall plot. Like we made circuits for every checkpoint of SFT using the datasets, and then and we also mapped some attention heads starting from the base model. Then we count the activate number of the activated attention heads newly activated, and this cohort plot of REPT shows out that SFT actually is some kind of stacking all the attention heads starting from the first checkpoint, which is checkpoint 100. And then the mapping of these attention heads, like the heat map of right one, shows out that the SFT heads are usually focused on mid to rate layers. And I saw one questions in the Zoom, like, oh, sure. Martin shows uh, one more questions, like, thank you for presentation. And so emergent attention head is like the that I answered to Professor O's question. Like it is not just head only activated in these LLMs, but it is some kind of emergent in the circuit, which is reconstruction for specific task of LLMs. So it is not emergent, it is already exists in the LLMs, but it emerged in those circuits, so it makes uh, some task activate or some task need these heads for its essential works. And I would like to go to the next one. Like, we would go to the next step, like GRPO. And GRPO helps to find the optimal reasoning passes. Like, unlike SFT, they dynamically activate and prunes reasoning heads. Like you can see that SFT was just stacking all the heads when the training passed, but GRPO dynamically like activate and then some pruned, some emergent heads are disappeared when the checkpoint become later. And heads rise and fall during training, and it reflects some kind of reward fluctuations and accuracy trends. And the final GRPO heads are fewer, targeted, and distinct from SFT heads. And those they embodies some explore and exploit trade-off. And quantitative analysis shows out that scaling activation, like scaling of 1.3, then improves math scores, but lower AMC and AIME performance, which is similar with the SAT's trade-off. And scaling down reduces AIME sharply, with slightly boost up some math and AMC. And qualitative analysis shows that GRPO enhances multi-step reasonings and symbolic manipulation at all the checkpoints. And large stage risk overfitting and instability, like trading agility for structural reasoning precision. They only use some specific like reasoning passes to solve every questions. And this is a similar cohort hit as cohort plots, and the right one like the following the trend reward, accuracy reward. The cohorts emerge, and then some disappeared heads are also exist, like born at the, checkpoint step 300 are going to decrease, going to disappear when it reaches to checkpoint 2000. And when we map these heads in the heat map, and this spread throughout all the layers and head indexes. And we pinpoint out the performance change, like for the checkpoint 100, then to one checkpoint 900. The GRPO training increased the performance with applying structured and step-by-step reasoning, which are also in the appendix of our papers, like the actual answers of these models. And also they use some effective solving strategies, but also this connection between describing solution and actual computation decreased its performance when it reached to checkpoint 2000. I didn't mention that the above figures, like three above figures, are constructed using the GRPO with dataset GSM per K and GSM AK, and then the down below three figures are constructed with mass 220. So that is why the checkpoints are different. And also for AI and benchmark, the GRPO training with GSM 8K introduced some systematical decomposed problem with mathematical principles, but it also shows some signs of overfitting, like rigidly applying only specific solving styles, which decreases its performances. And for the next, the last one is like thinking on-off model. It is some interesting insights coming from this think on-off model. Like those think on-off models activate thinking with chat templates. Like they can use thinking on with the think token in chat template, and they can use think off mode with uh, predefined template like think and done think tokens to do not to ask models to do not generate more think tokens. And the think of compensates some performance through enormous head emerging, which means like turning off reasoning triggers a broad resource efficient set of attention heads, and it indicates run the efficiency, like model compensates by selecting optimal computation routes. And the result of head intervention here, remove or scaling think of heads, affect hard benchmarks like AIME go to 30 to 20, which means decrease the performance, and uplighting redundant heads improve focus but may reduce adaptability or broader text. Some performance difference against coverage comparison shows that baseline think-of model perform better with larger sampling coverage, as its large number of active attention heads facilitates like some exploration of diverse computational pathways. Also, updating those or scaling down models lose flexibility locked into specific region paths, which means like when we update those heads in think-of, then some of the performance is even increased. Like, so this means like some redundant attention heads exist this thinking of circuits. And also for the next, we check the pass K and success K, which is basically largely used metric to check the performance of reasoning models. When the when the number of sample increased, then the think of mode, which is the baseline mode, largely over the performance is over than the other like updated models or scaled down models. But when we see the success key, which means like generation efficiency, like at the first time, which means the sample was too low, like 1 to 2 samples, then the updating increased its performances, while think up was slightly lower than the ablation version. But after the number of samples are increased, then the think of model continuously win other models as its enormous attention heads actually help to them to find out more passes in this large number of samples. And this is also aligned with the recent research from NeurIPS. Like they show that some RRs are just activate some initial thinking, activate and increase the performance of initial. Like if the number of samples are increased, then the base model also surpassed the performance of GRPS model. So this is also aligned with the insight of ours. And we also want to mention the limitations like model generalization. We only use the QAN models, and we are currently using Llama to re-implement our whole process. And some of the constraints of circuit analysis is also a problem. Like if you are not familiar with interpretability, it would be not a simple questions, not a simple themes, but like the analysis relies largely on just simple prompt-based circuits. And also, this approach may be vulnerable to polysemanticity, which is a hard problem of interpretability. And also, although there exists some kind of SAE, which means pulse autoencoder, largely used method of interpretability, and we can use it to construct circuits to avoid this some kind of polysemanticity problem, but it costs too much, and so this is why we use more practical way to compare various post-trained models. And our conclusion and future work is like in here, like mechanistic understanding of post-training. Would like to go to further step like making some more polished training policies, like encouraging targeted head activation rather than just uncontrolled head growth. Then use reward shaping to jointly optimize plans, and then leverage per head influence estimates to guide selective post trainings. And we hope this would be the next step of principled, interpretable, and robust post-training of effective reasoning strategies with the assurance of reliable and flawless executions. Thank you for listening my presentation, and if you have any questions, please let me know.
Thanks a lot, Yein, for that great presentation. The floor is open for any questions. While people ask theirs, I'll just ask one of mine. So this is about like, circuits and reasoning circuits inside LLMs. And there is a very similar work by Anthropic on transformer circuits. How does your work link to their work, or how is it different? What are the insights that are shared between both?
Yeah, sure. Like the circuits of entropic is actually the basic and related work of our circuits. Like they firstly use the circuits to trace their own model, like Claude, to trace all the thinkings based on the interpretable way of causal tracing. And they check the internal mechanism, like which attention heads move informations, or which part of uh, transformer, like for example MLP is the place of knowledge which stacked and storage edge knowledges, and they use circuit to distinguish and find out this kind of insights. And we are our used circuits like EAP-IG version of circuit is actually based on those circuit work of Anthropic. Yeah, so that is the circuit of Anthropic would be the baseline and the related work of our work.
Okay. Thanks for that answer. I have follow-up questions, not related to this one, but in general about the presentation. So for people who are less technical, you describe reasoning heads as if the model is growing new circuits. Can we think of this as a model developing specialized habits of thought?
Uh, can you ask again, like specialized?
Habit of thought. Like can we analogize?
Yeah, yeah.
Okay.
Yeah, yeah, sure, sure. Yeah. It would be possible like they also like using this kind of emergent heads only activate some strict and largely stuck only single listening passes or just using only the single version of like methodologies or mathematical expressions to solve questions. So it would be possible to like tracing this kind of specific uh, task specific, more task specific circuits. Yeah.
Thanks for answering my questions. Anybody else?
I still wonder as well. By the way, thanks for presenting great work. Super interesting. Can you remind me again how you identify these emergent heads? I think
Sure, sure.
I saw the slide, but I missed that.
Yeah, yeah, sure, sure. Like these kind of heads and circuits like it is not I would like to explain at first like it is not same as like showing that find out attention heads is not actually in it is not in the attention transformer models, and the circuit is just making the reconstruction of this kind of attention heads or MLPs in doing some specific tasks, and we just map these those kind of heads in this map like it is just a number counting or the yeah circuit distinguish from baseline circuits. Yeah, that is what I didn't explain specifically. Like we differentiate the reasoning model circuits and the baseline model circuits, and we found out only the attention heads coming in those reasoning models circuits, and we collect them, and then we mapped it to this kind of whole map of reasoning. And so yeah, these heads are only coming through the listening motor circuits, and it is not come with the base motor circuits. And that is why we distinguish this kind of or like post-trained circuits. Like we differentiate between GRPO circuits and base model, and we also distinguish between distillation version and base model. And yeah, the kind of things, and we map the index of those attention heads in this whole map. And also, I would like to say that the reason why we didn't check the MLP, like we for all
Or
the circuits, yeah, yeah,
maybe I need to clarify my question a little bit more. So I'm asking
yeah, sure.
how you determine, let's say, what is a good example? So on the very right left side, you have a red head there, right? Maybe that one, yes. How do you determine if that should be red?
The color means nothing.
No, no, no. I mean,
Yeah,
how do
yeah,
you
yeah, 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 sure.
determine that's emergent head for GRPO? What's the algorithm for that?
Ah. Oh yeah, the algorithm is like some systematical differentiation. Like when we do some GRPO for base model, we can collect all the checkpoints, and then we construct circuits for each different checkpoint with sampled answers of those kind of models, and so
What do
that
you mean
is
by
why
sampled
we
answered for these kind of models? What are
yeah.
these kind of models?
The model
GRPO model.
means checkpoints. Yeah, GRPO checkpoints, which
Okay.
is a post-trained models. And then the sampled answer is like this kind of prompt, like as the circuit construction is done with the input prompt and to predict what comes next for first what comes for the uh, first token of output, and that is why they trace the internal mechanism of transformers LLMs, and so that is why we use the sample prompt samples. And then for those kind of GRPO, for these checkpoints, we use AIME questions, and then what would be the internal mechanism of this kind of GRPO checkpoints to predict the output token think and the next one. Then we can reconstruct the internal mechanism of thinking process. So that is how we make the reasoning version of circuits. And then we also do the same work with the base model, like use same question of AIME, and then we trace the model's answer right after the think, and then it can construct the circuit, which is a graph for those base models. And we just differentiate all the nodes of each circuit and then find out what is the specific nodes only shown in the each different checkpoints or each different post-trained circuits. And that is how we map these GRPO heads, which is distinguishable, which is not shown in every other circuits of this method. Is it
So there,
okay?
there are a lot of moving parts here. So one is essentially whether you use the prompt, these special prompts, right, that you came up with, or whether you use the baseline prompts. So that's one kind of differentiation that you're looking into. The other
Mhm. Yeah,
differentiation
yeah.
is across different checkpoints, right?
Yeah, sure, sure.
So I don't, it's hard for me to imagine like how these differences are eventually coming together.
Yeah, sure, sure. Like it would be like a little bit different for like not familiar with this kind of circuit analysis. And so yeah, uh the paper explained more about this kind of things. And so is there any like well hard to understandable part? Like I would explain more. Yeah.
Hmm. Um, I would take this offline and ask you further questions on Slack.
Okay, thank you.
In the meantime,
I'm
there was
sorry
another
to yeah.
question, right?
I think it is for the Mukund.
Mukund.
Yes, let me take this up. So, thanks, Martin, for your comment. Could these Olympiads be used as multilingual benchmarks for LLMs, or are they more logic benchmarks? So, this is a good question. Um, to answer the first part, yes, but that is not the focus of our study. We were trying to study what makes puzzles more difficult or less difficult. But in general, I think these are good benchmarks for linguistics, multilingualism for sure, low resource languages, and reasoning in general. Benchmark. The issue with this benchmark is that none of these languages are in the training data. And thus, you cannot really benchmark them very easily because a lot of the training data is also black boxed and we cannot really know what's going on inside in training, like closed source models, etc., even for open source models. So there is only one issue in this benchmark in terms of memorization. Otherwise, this benchmark can like address a lot of concerns simultaneously. In terms of being specifically a multilingual benchmark, yes, because some of the lower resource languages belong to a family of languages which might have a higher resource language or a mid-resource language, which you might want to work with. For example, if you are working with Assamese, which is a lower resource language than Hindi, and Assamese is used as a linguistics Olympiad puzzle problem, then you can maybe approximate how other languages in that region or in that language family can like work. So yes, in that sense, multilingual benchmarking can be done through linguistics Olympiad problems. In terms of being a more logical benchmark, I think one needs to sit down with these puzzles and like annotate like with it for linguistic features. We
Mm.
need to annotate the logic portions of it to like make sure this benchmark works like you would want it to as a logic benchmark. But yeah, this is the answer to your question. Hope that addresses your questions. Yeah.
Thank you so much, everyone. So now the time is up actually for the first session. So I already wish to thank the first two speakers for sharing their time and presenting great work.